Let me take it a little bit more mathematically, and that's how I go. So I have L1 or L2 or L3 all the way up to Lk, and I am given a M. My resolution is L1 or L2 or Li minus or Li or Li plus 1, deleted L2 or Lk. Okay, let me make it I minus 1 and I plus 1. Where M and Li are opposites. So if M is true, if M is studies AIR1, Li is not studies AIR1. And I've already seen an example of it, and I've already proven that. So just fill it in. It turns out this is called as a unit resolution. Where I resolve using 1 unit M. So now I'll generalize to what is called as a full resolution. Here I'm given L1, L2, L3, Lk, and I'm also given M1, M2, M3, Mn, and I cut two things which are opposite of each other. I cut Li and Mj. Last time I made a mess, so I'm writing it down beforehand. So Li minus 1, Li plus 1, or Lk, or M1, or Mj minus 1, or Mj plus 1, or Mn. I'll just give you proof now, it will be obvious. Li and Mj are opposite. Studies AIR1, not studies AIR1. That means the only combinations possible are that number one, Li is true and Mj is false. If Li is true and Mj is false, so Li becomes true around over here. So this naturally becomes true. L1 or L2 or L3 all true. True or anything is true, and that anyways was given to me. And Mj becomes false. So Mj becomes false. Now this entire thing is a fact. It's given to me. It's a rule. So if Mj is false, false or anything is just that anything. So Mj is false, I can just take it out. So it becomes M1 or M2 or M3 or Mj minus 1 or Mj plus 1 or Mn. Now Mj is false, that means the onus of make this thing true is upon this little term around over here. And this has to be true, otherwise this fact will become false. And if this fact will become false, my rules don't hold good. God, my rules hold good. Grounding, my rule correct. So if this is true, so if this little thing is true, that means this is true. If this is true, then true or anything is true. So this will hold good. The other thing that you could say is the other combination is converse. If this is false, this is true. There's no other combination because Li and Mj are opposite of each other. So if this is false and this is true, what really happens around this time is Mj becomes true, and because Mj becomes true, this is always true, doesn't matter. And because this is always true, doesn't matter, Li is false. And if this is false, a false can always be removed. False or anything is that anything. That means it's L1 or L2 or Li minus 1 or Li plus 1. I removed Li or Lk. This has to be true. Otherwise, this fact will become false. If this is true, then this is true. If this is true, this whole is true. Otherwise, rule will get broken. Now the good thing is that this is the only way by which this algorithm works. Can you have AND in resolution? No. Can you have implies in resolution? No. Can you have bijection in resolution? No. So it appears that with resolution I can only take one kind of input, which is true, but then you already know that anything, so the sentences can only have a and, or, not, implies, bijection. All of them can be reduced to just and, or, and not. This is not A or B, and this is A implies B and B implies A, and then A implies B is not A or B, B implies A is not B or A, so you can reduce it to and, or, and not. You know the De Morgan's duality principle, so you can take not inside, so not only comes up with the individual elements, and everything can be expressed in the form of a conjunctive normal form Boolean algebra, which is A or B or C and D or E and F or G or H. And then you say statement number 1, A or B or C, and elimination, statement number 2, D or E, and elimination, statement number 3, F or G or H, and elimination, where these are my statement, or what I say, these are my clauses. So even though it only works with this or thing, remember that anything in logic can be converted into a conjunctive normal form, provided you know what are the rules of the Boolean algebra, not a part of this lecture. And hence I could resolve anything up. The last thing is, which again is obvious, sometimes in resolution you have a funny input, A or B or C, and you have A or not B. So let's try to resolve this up. B cut each other, so B goes from here or C, and not B goes from here or A. A is twice. This is just equivalent to me saying A or C, and this is called as factoring. So if something comes in resolution twice in the resolvent part of it, remember this is also what is called as what you resolve, the resolvent. If anything comes up twice, you could as well remove one of them up. It makes absolutely no difference. Now, we've only taken a solved example about how to apply resolution to check if the theorem alpha holds or it does not hold. Now what we'll do is we will write down a short algorithm, and let's see what happens in that short algorithm. I again need not tell that to you, so you should be able to write it down again. So we say the propositional logic resolution. I have been given my knowledge base, which is some clauses, clause 1, clause 2, clause 3, facts, rules, whatever. And I have been given alpha, which is the theorem that I would like to prove. Now, does this happen or does this not happen? So, of course, I temporarily add not alpha to my KB, and then I just pick up any two clauses and I resolve that up, and whatever is the resolvent, I put it to my new set of clauses. So let's make a set of clauses. So to clauses, where initial clauses are nothing but your entire KB. So I take up any two sentences for CI and CJ for every CI and CJ in clauses. I say get a list of everything by cutting each pair of negative whatever you get. So I say R is equal to resolve when CI gets resolved with CJ, and I just add it to a new set of clauses that I know of. So let me say new as empty initially. Now all I need to do is I need to do it infinitely often. I'll get something, I'll add it to my set of clauses and I'll restart. I'll take a new clauses again. Every clause CI and CJ could be checked infinite number of times, and therefore I put it inside an infinite loop. And I add my new clauses over here. Now it's an infinite loop. Of course, I'll need to break. There will be two breaking criterion, one for success and the other for failure. We know both of them. So let me add the first one over here. So if R contains empty, that means I got a situation wherein I could not satisfy the model empty, like last example, honest or not honest are one, empty. So I just return a true. And if my clauses start repeating themselves, if new is a subset of clauses, so I did not add any new information. Whatever I knew was already known. If I did not add any new information, then I say that everything which could have been done has already been done. So I just return a false. That means there's at least one solution which is possible. Now again, if you are thinking of heuristics, the entire thing to do with AI, can I use heuristics? Yes, you should be using it. In which order do I select C1, C2 at every time? Which specific C1, C2 should I select? Heuristic. So that you go closer towards trying to prove it as empty. The moment you prove that empty, you know that your knowledge base entails alpha, or alpha is proven. I've got a bit of a task around over here, which is of course not to prove the optimality. There's no optimality in CSPs. To prove the completeness and the soundness that yes, this actually works. Let's talk about completeness first. Every time I add a new information, every single time I add a new information, if I cannot add a new information, I just terminate. How many information can I have? How many resolvents can I make? My symbols are finite, and because my symbols are finite, permutation and combination, school level, you can calculate how many resolvents will be possible. More than that, my knowledge base will also not only take it. Clauses is a set. It doesn't take things which are repeated. It's not an array that takes things which are repeated. At some point of time, I would have added all the resolutions which are possible. And after that, I'll have no other choice but to repeat it. That's what I previously said. Graph search, not a tree search. Any algorithm is complete. There are finite states. At the end, what? You would have visited all the states. Your clause would have all the states. You have to terminate. There's nothing you can do. All the clauses have been generated. However, this doesn't really prove soundness, which is the fact that it actually works. And that's a harder task. So let's see that the algorithm actually works, and let's try to take an intuitive proof. Without loss of generality, I mention my symbols as P1, P2, P3. So this is honest AIR1, on studies AIR1, all those big fat. So I just named them P1, P2, P3 all the way up to Pn. Simpler terms, and there is an order. Doesn't matter what the order is. It's up to you. Now, if I can prove that the problem is satisfiable, that means I can get at least one solution that satisfies and that means not alpha is satisfiable, that means alpha is not valid. So that's what I have to do. I have to prove that no solution is possible. If I get one solution, not alpha is satisfiable, alpha is not valid, it's not sound. So I go on an expedition and I say I will give one solution by assigning in either true or false to all P1, P2, P3 all the way up to Pn. I'll give at least one solution. If I can give one solution, the model is satisfiable, not alpha is satisfiable, alpha is not valid, it's not sound. So let's see if I can give a solution. Let's go directly to Pi, assuming everything before Pi has been assigned either true or false. So there's no problem with that. So I'll iteratively go. First I'll assign P1, then P2, P3 all the way up to Pi. I say directly switch to Pi. Everything before has been assigned. And in terms of clauses, I only take clauses which have Pi or not Pi. And everything else which is P1, P2, P3 all the way up to Pi minus 1, but nothing which is over Pi. So I have P1 or P6 or P7 or Pi, nothing which is over Pi. It's in assorted order. P2 or P4 or P8 or not Pi, nothing over Pi. I only take those clauses. If you don't have such clauses, believe me, you could randomly assign true or false, doesn't matter. Now, every time I satisfy a clause, I delete it up. I need to satisfy all the clauses. True or anything is always true, irrespective of whatever. So my problem is I've got a set of clauses C1, C2, C3, C4, C5. Two of them are given around over here, either of them. The moment the clause is satisfied, I just delete it up. A clause needs to be satisfied by a model just once. It's on true. The moment you get true or anything, you don't need to care what is true. So if P2 was true, I would have said true or something. It doesn't matter what is Pi, true, false. If P2 is true, this is entirely true. If P6 is true, it is P1 or true or something. It doesn't matter what are P1, P7, P1. It's true. It's deleted. So when I do the assignment in a layer by layer, P1, P2 by manner, anything which becomes true at any point of time, I'll just delete. Okay, it has been satisfied. And I'll stop when all P1 to Pn have been assigned either a true or a false. And all C1, C2, C3, C4, C5, all the clauses are valid. Or they all end up being true. The moment they become true, I just delete that up. Now, I'll either get this or I'll get this. If you get this, then say Pi is equal to true. If you get this, then say Pi is equal to false. And just go ahead. Just go ahead. Now, what if I get both of them? So let's say this is some C6 and this is some C10. Now, if I assign Pi as true, this becomes true, but this becomes false, and everything is less than Pi, so there's no way to make it true. If Pi is assigned false, then this becomes true, I delete that up, but Pi becomes false. There's no way to satisfy that up. I'm again in a trouble. Now I place a specific definition on Pi. So I say Pi is the first point of non-satisfiability, that means when I assign P1 something true or false, P2 something true or false, P3 something true or false, Pi is the first point where I fail. So the first point where I fail is Pi. Now if C6 is there, clause 6, clause 10 is there over here, it definitely means the resolution of clause 6 and clause 10 would be in my set of resolvents. Let's resolve that up. Pi and not Pi will cut each other. I'm no longer doing it the complete way. So it will become P1 or P6 or P7. Pi will cut P2, P4 or P8, where of course Pi is greater than 8. Now this is false, otherwise I would have deleted that up. Before Pi this is false, this is also false, otherwise I would have deleted that up. C10 wouldn't have been in my database. Both are in my database when I'm assigning Pi. That means this also did not become true, this also did not become true. That means this is in the database, this is in the database, which means this is false, or C of 6R10 is non-satisfiable. However, Pi is my first point of failure. How did I fail at P8? Contradiction, which goes eventually to prove that the algorithm is sound. If I get null, of course, there is no way to satisfy that up. If I don't get null, the model is 100% satisfiable, which means my definition that not alpha is satisfiable or not alpha is invalid is completely correct. How did I prove it? Proof by contradiction again. It's funny, resolution itself is proof by contradiction. To prove the algorithm, there's another proof by contradiction. So I said that, let's say that P1 to Pn is satisfiable. I had to prove that. So I say it's not satisfiable. All I did was, I took a Pi as a first point of entry, the first point of unsatisfiability. I did not get any such first point of non-satisfiability, and because I did not get that, that means the model is 100% proof by contradiction satisfiable. If it is 100% proof by contradiction satisfiable, that means my algorithm is returning the correct thing.